Hello everyone, welcome to Vishesh Educational Videos. In this video, I'm explaining semaphores, one of the important concept in operating system. If you're not subscribed to my channel, please subscribe to my channel. To get the notification of my new videos, please click the bell icon and please share my video with your friends. So let me start the explanation. So before understanding what is a semaphore, here I am considering a simple scenario. In that scenario, we have to assume that two processes wants to access the same data simultaneously. But here we have a problem. When two processes wants to access the same data simultaneously, we have a problem. What is that problem? When two processes wants to access the same data, one of the process may access the incorrect data, right? So one of the process may read the incorrect data from the other process. This problem is nothing but race condition, right? When we allow two processes to access the same data, that is shared data, concurrently, there is a chances, right, that one of the process may read the incorrect data, right? So how to overcome this problem? How to assure that two processes, right, read the correct data? How to do that? So to overcome this problem, we need to design a protocol, right, that is going to implement critical section problem. So what is a critical section problem? So critical section problem, right, it will implement some synchronization. How it is going to implement synchronization means, so when a process wants to access the data, the process that is want to access the data should enter into the critical section. So what does that mean? So when the process is in critical section, it can do some activities like updating a table, writing a file, so whatever the activity it may be. So process has to do that activity by entering into its critical section. When if other process wants to access, or if other process wants to do the task in a critical section, that is not possible. According to the critical section problem, right, when one process is executing in its critical section, no other process is allowed to execute in its critical section. So thereby, right, we can achieve some synchronization. Here, when one process is executing in its critical section, the second process will wait until the first process finishes the execution. So then it will start its execution. So thereby, both the process is going to read the correct data. Getting, guys? So both the process is going to read the correct data. Now, what are the three properties that should be met in a critical section? The first property that should be met in a critical section is mutual exclusion. So mutual exclusion means if one of the process executing in its critical section, then other process can't be executing in its critical section. So after that process finishes the execution, then that process can enter into its critical section. So at a time, only one process should execute in its critical section. So thereby my data is protected. So if you want to know more about the critical section, so you can refer my previous video, where the link for that video is given below in the description section, right? So now progress. What is a progress? So only the interested processes, that means only the process that wants to enter into the critical section should give a chance. If a process is not interested to enter into its critical section, just leave them, no worry. Even if a process is interested, then only you have to give the chance to the process to enter into its critical section. Now what is bounded waiting? So bounded waiting means we have to limit the number of times that a process enter its critical section. Suppose if any one process is executing all the time in its critical section, the other process can, right, may not get a chance to enter into its critical section. It should not happen like that. Every process get the equal opportunity. Every process should get the equal opportunity. So when you're designing a critical section problem, you have to implement in such a way that these three conditions should met properly. Now, how to implement this critical section problem means, so either you can use PETERSON solution, where it's a software solution to the critical section problem. So if you have any doubts related to PETERSON solution, you can refer my video. The link for that also is in the description section. So now PETERSON solution is a software solution. Now after that we can implement some hardware based solutions also. So in hardware based solution there are two types: test and set and swap instructions. If you want to know more about test and set and swap instruction, a link for that video is also in the description section. So now I can implement critical section in two ways: PETERSON solution, and in hardware based solution I can implement it in test and set instruction or using a swap instruction. But there is a problem here. What is the problem? Right? This test and set, swap instruction or PETERSON solutions, these are complicated for application programmers to use. That means for the programmers it will be difficult for them to implement these solutions. So what is the solution for this now? So PETERSON solution, it is difficult to implement for the developer. Test and set and swap is also difficult to implement for the developer. So how to overcome this means, we can use some synchronization tool called a Semaphore. So Semaphore is also one of the technique to achieve critical section problem solution for the critical section problem. Semaphore is also one of the tool for the critical section problem. Right? Now I will explain what is a Semaphore. So what is a Semaphore here? So simple, very simple. A Semaphore is an integer variable. It's just an integer variable, right? You can see here, see the highlighter here. This is just a variable. Semaphore is a variable. Yes. What type of variable it is? Semaphore. It is an integer variable. That's why int s. Now, it is just a simple variable you can use. But the problem here is, once the Semaphore is initialized, after the initialization of the Semaphore, you can use the Semaphore, or you can access the Semaphore by using only wait and signal instructions. Right? Now you can see here, suppose if you initialize the s, that is Semaphore, to 1, then if you want to change the s value to 4, you can't directly change this. Right? So if you want to change the s value to 4, you can't directly change this. Right? What we have to do means, we have to use wait and signal instructions to do this. Getting, guys? I will show that how we are going to use wait and signal to change the contents of the Semaphore. Getting, guys? So Semaphore is just an integer variable. After initialization, we can't change the values of that Semaphore directly. If you want to change the value of that Semaphore, you have to use wait and signal, right? Wait and signal instructions. And one more thing, wait is also called as P, signal is also called as V, one and the same. Getting, guys? Now I will show you how to use wait and signal to alter the contents of the Semaphore. Getting, guys? Now, so this is the definition of a wait and signal here. So this is the definition of the wait, right? It is very simple. I will explain this, no worries. So this is a signal. This is the definition of the wait. This is the definition of the signal. In simple words, wait, what it does means, it will decrement the Semaphore value. Wait will decrement the Semaphore value. Signal will increment the Semaphore value. Very simple. Getting, guys? So now we will see this. So see here. So if s is equal to 1, I'm taking the example here. Here if you want to change the Semaphore value, I told you you can change the semaphore value using only wait and signal, right? So I will show you that how I am going to change the value of semaphore using a wait, and I am using a signal also. See here, suppose my s value is 1. So in wait, I will check the condition, while condition 1 lesser than or is equal to 0, because s value is 1 here. The condition is what? Condition is what? False. So it will go here, it will decrement the s value from 1 to 0. Getting, guys? So here what I did, I changed the semaphore value from 1 to 0 using a wait. In the same way, I will change the s value using a signal. See here, the s value is 1. So I will enter inside this, I will increment the value from 1 to 2. Now what I did, I changed the semaphore value from 1 to 2. Getting, guys? So in this way I can use wait and signal to change my semaphore value. Here in the wait I decremented the value from 1 to 0, but in the signal I incremented the value from 1 to 2. Getting, guys? Now, so one more important thing you have to remember here is all the modifications to the integer value of the semaphore. Whatever the modifications you are going to do for the semaphore, here you did a modification, right? From s value changed from 1 to 0, here from 1 to 2. So these modifications must be executed indivisibly. What is the meaning of this? It is very simple. See here, when one process modifies the semaphore value, no other process can simultaneously modify the semaphore value, same semaphore value. See here, here the wait is changed the semaphore value from 1 to 0, right? At the same time, concurrently, signal is also can't change the value of the semaphore from 1 to 2. No, first either wait should execute or signal should execute, or first signal should execute, then wait should execute, like this. So both of them can't execute simultaneously or concurrently. Only one should execute. Either wait should execute or signal should execute, or signal should execute, next wait should execute, like that. Both of them can't execute simultaneously. That is very important. Getting, guys? See here. Now, how to use this wait and signal to solve the critical section problem? You can see here, this is the solution to the critical section problem, but this solution contains semaphore, right? This solution contains semaphore. So this is the code for this. So this is the simple code, very simple code. This is the code to solve the critical section problem. I will explain this code now. Very simple. You can see here, the code is in the left side, see the highlighter, and the definitions of wait and signal is in the right side, and this is the procedure. This is the procedure. Getting, guys? Now, see here, consider the two processes here. P1 is one process, P2 is another process, because I have to explain the critical section problem, right? That's why I consider two processes here. So one is P1 and another one is P2. So now see here, this is the code of the critical section. Now P1 will use this code. We will see this entire steps, right? Now I will initialize s to 1. So what is the value, initial value of s? The initial value of s is 1. Initial value of s is 1. Which process is executing now? P1 is executing. So it will go inside the wait function. So this is the definition of that wait. See, so what is the value of s? 1. Now it will come inside the while loop of the wait. So what is the condition there? While s lesser than or equal to 0, while s lesser than or equal to 0, what is the value of s here? 1. So 1 lesser than or equal to 0, 1 lesser than or equal to 0, what is the condition there? No, false. Condition is false. So while condition is false, so that's why s will be decremented by 1. So s will come out of the loop. See, yes, condition is false, that's why s will come out of the loop. There is no code for the while loop here. While loop doesn't contain any code. That's why when the condition is false, so s will come out of the loop. Once it come out of the loop, what it will do? S will be decremented by 1. See, s minus minus. So P1 comes out of the loop here. Condition become false. So P1 come out of the loop and it will decrement the S value by 1. S minus minus. So what is the S value now? P1 changed the S value to 0. P1 changed the S value to 0. But remember, after changing the S value to 0, P1 is still executing in its critical section, right? P1 is still executing in its critical section. It is still in the critical section. It is right. So now assume that P2 will request to enter into its critical section. Right? Now P1 is changed the S value from 1 to 0. You know that weight is decrement the value. That's why it decremented the value from 1 to 0. So that is P1 is again still it is in the critical section. Now when P1 is still in its critical section, P2 will request to enter into its critical section. P2 will try to enter into its critical section. Now we will see whether P2 is allowed to enter into the critical section or not. Now what is the S value there? S value is 0 because S value is changed from 1 to 0 from P1. So now S value will become 0. So again P2 will enter to the weight. P2 will enter the weight statement. So what is the condition in the weight statement? While S lesser than or equal to 0. Now what is the value of S here? 0 lesser than or equal to 0. True. The condition become true. The condition become true. So when the condition become true, the P2 what it does? Now P2 keeps on looping in a while. So P2 doesn't come out of the loop because the condition is true, right? That's why. So P2 what it will do means P2 will keeps on looping in a while until P1 increments S value using a signal. So getting guys, so P2 tried to enter into the critical section, but it is not possible because S value this condition became true. So that's why P2 will what it will do, it keeps on looping in the while. It keeps on looping in the while. It can't enter into its critical section. So P2 now what it should do means P2 should wait until P1 finishes its critical section. P2 should wait until P1 finishes its critical section. Now, so see here. Now, if P1 comes out of the critical section, P2 can enter it, right? We will see here. Now, P2 keeps on looping, you know that. So P1 increments the value using a signal. So it will in the critical section. While exiting, P1 what it will do means, you can see signal value is what? It will increment the S value. Now what is the S value now? 0. Again, S value will be changed to 0 to 1 by P1. Yes, P1 changed the S value from 0 to 1. Again, it will change the value S from 0 to 1 P1 while exiting. Now, see, now if P1 comes out of the critical section before exiting, P1 use the signal to increment S value. So P1 changes the S value to 1. So P1 before exiting its critical section changed the S value to 1 and P2 is still looping in the while, right? So when the P1 changes the S value to 1, what happens means P2 can enter into its critical section. Why? See here, S value become 1, right? 1 lesser than or equal to 0, condition false. So P2 can enter into its critical section. Getting guys? So P2 can enter into its critical section. That is S is equal to 1. S is equal to 0 means condition was true. Now again S value is changed to 1, right? Now P2 comes out of the loop. It can't keep it, now it doesn't loop. It comes out of the while loop and it will enter into its critical section and it will decrement the S value. So P2 can enter into its critical section. So one thing you can observe here. So first thing, P1 was executing in its critical section. When P1 was executing in its critical section, P2 requested to enter into its critical section, but it was not possible. P2 can't enter into its critical section. It keeps on looping in a while. When P1 finishes its execution while exiting, it will change the value of S to 1 again. When the value of S becomes 1, the condition false. The condition in the P2 become false. Now P2 can enter into its critical section and it can execute here. So getting guys, so here either P1 can execute or P2 can execute at any point of time. So mutual exclusion holds good here. So what is the condition of the mutual exclusion? So if only one of the processes is executing in its critical section, the other process can't execute in its critical section. So see, while P1 is executing, P2 waited. Once the P1 is completed its execution, P2 enter into its critical section. Getting guys? So mutual exclusion holds good here. Getting guys? Now we will check whether the progress is going to hold here also. Yes, progress we will check. What is the progress? Progress means only the interested process should allow to enter into its critical section. See here P1 is interested, I allowed it. Again P2 is interested, I allowed P2 to enter into its critical section. Here both P1 and P2 have interest to enter into its critical section, right? That if any process, if suppose if P2 don't have any interest, no worries, I just leave it, I can just leave it. But here what I did, P1 is also interested, I allowed it. P2 is also interested, I allowed it. Thereby progress is satisfied here. I am allowing only the interested process to enter into its critical section. Getting guys? So wait, if you have any doubts, please post your doubts in the comment section, right? So now progress is also satisfied. Now bounded waiting, I will check whether bounded waiting will satisfy or what. See, so see if initially P1 is executing in its critical section. Now P2 tries to enter into its critical section, but P2 can't enter it because condition is false. It keeps on looping, you know that, right? But while exiting P1 after completing the critical section, it changed the value to value of S to 1, right? So P2 can enter into its critical section. So you are seeing here P1 after completing, P1 is getting the chance to P2 also. P1 is giving the chance to, sorry, P1 is giving the chance to P2 also, right? Yes. Again, after P2 completes the execution, again if want, P1 can enter into its critical section. Again, P1 can give the chance to P2 in the second iteration also. You can see here, P1 is also getting the opportunity, P2 is also getting the opportunity. Only one process is not holding all the time. P1 is also getting the opportunity, P2 is also getting the opportunity, right? You can see that. Earlier P1 was executing. Once the P1 is executed, it will P2 can enter into its critical section. In the same way, again after P2 completed the execution, P1 can enter into its critical section one more time. Again P2 can express its interest. Once the P1 is executed in its critical section, again P2 can enter second time also. So here P1 and P2 are getting the equal opportunities. So here bounded waiting is also satisfied. Getting guys? So this code satisfy all the three conditions. This code satisfy all the three conditions. This code satisfy all the three conditions: mutual exclusion, progress, bounded waiting. Getting guys? Very simple. Now what are the different types of semaphore? In semaphore, mainly there are two types, right? One is a counting semaphore and one is a binary semaphore. Very important, listen here. Binary semaphore uses the value 0 and 1. The value of the binary semaphore is what? 0 and 1. But value of the counting semaphore can range from minus infinity to infinity. There is no restriction there. That's why counting semaphore is unrestricted domain. Unrestricted domain means minus infinity to infinity. But binary semaphore means what? Only two values. It is restricted to two values, that is 0 and 1. So this example what I explained now, this is the example for a binary semaphore. You can see here what are the values I used for the S here. 1 and 0 only. See, 1 and 0 only I am using. I am not using any other values. So this is the example for the binary semaphore. I am using only 1 and 0. Getting guys? So binary semaphore will use only two values. Whatever the example I explained now, that is an example for a binary semaphore. Here I used only two values for S, 1 and 0. Getting? Now, on one more important thing, binary semaphore is also known as mutex locks, because using this binary semaphore I can provide mutual exclusion, right? You have seen that. This is the explanation of mutual exclusion only. Either P1 can execute or P2 can execute in its critical section at any point of time. So here, using a binary semaphore, what you are doing? You are satisfying the mutual exclusion condition, right? Along with other two, you are satisfying mutual exclusion also. That's why. So sometimes semaphores, binary semaphores, also called as mutex locks. Mutex locks. Getting, guys? Now, what is another type of semaphore? This is a counting semaphore. So binary semaphores are mainly used to provide mutual exclusion. Mutual exclusion. Now, counting semaphore, why we use this? Counting semaphore mainly used for resource allocation. Remember that? So this semaphore, binary semaphore, used for providing mutual exclusion. Counting semaphore, so this is the example, you see that, right? Mutual exclusion. So counting semaphore, why we use? To allocate the resources. Now we will explain how we are going to use the counting semaphore to allocate the resources. See here. So first I will explain this process, and I will take the example. Now the semaphore, so you know that counting semaphore are used to mainly allocate the resources, right? When there are finite number of instances, that means when there are finite number of resources, you can use this counting semaphore to allocate the resources to the processes that request. See here, the semaphore is initialized to the number of resources available. So for the first step, the semaphore value is now, what is the value? Semaphore value is the value of the number of resources that is available. See, now I will initialize the semaphore. This is the first step. I will initialize the value of the semaphore to 5. That means how many resources are available here? 5 resources. So S is equal to 5. I have 5 resources. Assume that I have 5 printers. I need to allocate that 5 printers to different processes that request that printers. So how many printers I have? How many resources I have? 5 resources I have. Sorry. So see, this is the first step. Now what I will do? Now when a process, right, when a process wants to use a resource, that means when a process request for the resource, what I will do? I will use a wait operation. When a process request for a resource, I will use a wait operation. You know that wait operation, what it will do? It will decrement the semaphore. It will decrement the semaphore. See, so when the process wish to use the resource, I will perform the wait operation, so thereby decrementing the count. What it does, it will decrement the count. Now I will assume there are 5 resources. Now I will assume one process wants to use the resource. One process wants to use the resource. Earlier, how many resources were there? 5 resources. When one process wants to use the resource, I need to decrement the value. I told you, right? When a process wants to use the resource, you have to use the wait. That means wait has to decrement. Wait decrements the value. You know that. Now S value is changed to 4 from 5. That means one process is using the resource. Still 4 printers are remaining. Again, if the second process wants to use the resource, again I will decrement this. Again the value of S will reduce from 4 to 3. Now 2 processes are using the resource, still 3 remaining. Right? Getting, guys? Again, if another process request, I will decrement 3 to 2. Now 3 processes are using, still 2 remaining. Again I will decrement from 3 to 2, 2 to 1, like that. So every time when a process request, I can decrement the value of a semaphore. Now when a process releases a resource after the completion of the task, process can release a resource. It doesn't want it, right? When a process releases a resource, what I have to do, I have to perform a signal. That means I have to increment the value of s. When a process requests a resource, I will decrement the value of s. That is right. When a process releases a resource, I will perform a signal. That means it will increment the value of s. Now assume that one process that is requested the resource, now released it. Now again the value of s changed from 4 to 5 because that resources is released. That only one process is used in this example, right? That's why one process released it, the value of s is changed from 4 to 5. Now see here, once the value of s becomes 0, what does it mean? If the value of s becomes 0 means all the resources are in use. So here the value of s is 5, right? So 5 becomes 0 means all the 5 resources are in use by different processes. 5 processes are using 5 resources. It's not a rule that 5 processes should use 5 resources. Don't get confused. Only one process can request all the 5 resources also. That is also a possibility. Don't get confused here. When s, just remember that when s value becomes 0, you just know that resources are in use. Here s value 0 means all the 5 resources are in use by one of the process, right? Now getting, guys? Only one process can request all the resources, or different process can request all the resources. It is both are possibilities only. No, right? Now if s is 0, the resources are in use. Now you can ask a question, sir, here s is 0 is there. Now if any process wish to use a resource, what should it do? Because s value is 0, there is no resource, all the resources are in use. Now the another process wants to use the resource, what it should do means the process should wait. The new process that is requesting the resource should wait. How much time it should wait? It should wait until the count become greater than 0. That means the count of s should be greater than 0. The count of s should be greater than 0. Either it can be 1, 2, 3, 4, 5, whatever the value it may be, but it should be greater than 1. Greater than 0. If it is 1 means 1 resource available. If 2 means 2 resource available. If 3 means 3 resource available. If 4 means 4 resource available. If 5 means 5 resource available. Getting, guys? So even if it is 1 also, greater than 0 only. Even if it is 5 also, greater than 0 only. So getting? So if the value of s is greater than 0, right, then that process that is waiting for a resource, the process waiting for a resource can use that resource. Getting, guys? Very simple, right? So that's it, guys. If you have any doubts, please post your doubts in the comment section. Thank you for watching the video. Please don't forget to subscribe to my channel. Please click the bell icon to get the notifications, and don't forget to like and share.